Thanks everyone for joining today's Exida webinar on alarm management and making the most of alarms as a layer of protection. Please let me know via the feedback signal if you're having any trouble hearing me. My name is Todd Stauffer. I'm Director of Alarm Management Services here at Exida. And today what we're going to talk about is how to design and analyze alarms that form a safety layer of protection. And we'll look at the different factors that go into this, and then we'll look at how we can deliver on the risk reduction that our design assumes, taking a page from the new ISA standard on alarm management and looking at some best practices there. So one of the main motivations or purposes behind this presentation is really to raise the awareness of how alarm management and functional safety go together. They really do go together hand in hand. Alarms are a layer of protection, or can be a layer of protection, used in conjunction with a safety instrumented system to prevent a process upset from escalating into an accident. Safety instrumented systems, on the other hand, generate alarms, or can generate alarms, to indicate that a trip has occurred, or to indicate a degraded mode. Now, poor alarm management has been a major contributor to some of the worst process safety accidents kind of on record in recent history. Certainly what comes to mind is Texas City, the refinery, and then also the Buncefield Oil Depot in the UK. And we're going to talk a little bit more about Buncefield because it's a great example for illustrating layer protection analysis and how alarms go together. Now, the scope of this presentation is primarily focused on alarms that provide a quantitative level of risk reduction, meaning they're part of a layer protection analysis. They're safety IPL alarms. But the best practices, certainly related to the ISA standard, work for any alarm that provides a level of safety or supports safety. So this discussion supports quantitative and qualitative risk reduction provided by alarms. Now, one of the most important things to take from this presentation is that the design and performance of the alarm system affects the integrity of the safety functionality that's provided by either the operator or the safety instrumented system. And here we're looking at some actual plant data from 2005 from an ethylene plant in the Houston area, and we can see the number of alarms per day before an alarm management program was implemented and then after the program was implemented. So the question is, how comfortable would you be as the safety system designer that a safety IPL alarm, or safety critical alarm that occurred with the performance on the left-hand side, how comfortable would you be that the operator would see that alarm and respond to it and not miss it? Certainly, you'd have less confidence in that than if the alarm system was performing as we see on the right-hand side. And that's part of what we want to talk about, how the performance of the alarm system can affect the actual level of risk reduction that would be provided by a safety IPL alarm, an alarm as a layer of protection. It may reduce it or it may eliminate it altogether, which would mean that the level of risk that you actually have is higher than what you thought you have and may increase the risk above your tolerable level. Now, if you know this and you realize this, you may make some design modifications to either implement additional safety instrumented functions or to increase the SIL level of those SIFs that you do have. But of course, we all know that can be expensive, that costs money, and increase the burden on our testing, our proof testing. Now, alarm overload, or the number of alarms per day, is not the only alarm management issue that affects the operator and influences their performance and the likelihood or the unlikelihood that they'll respond to an alarm. There's also other symptoms of alarm management performance issues. Certainly if the operator's console is full of alarms all the time, and you've got alarms that go in and out of alarm with a high frequency, if you've got situations when one event occurs and you got multiple alarms always being presented to the operator, those situations are going to get in the way of the operator making a clean, clear view of what's going on and an accurate response. Now, when it comes to the operator, if they don't know how to respond to the alarm, or we don't give them enough time to respond, that's also going to affect their performance as well. So, if I skip the slide here we go. Nope. So now let's look at what can go wrong, what can possibly go wrong. And as an example, we're going to look at the Buncefield Oil Depot. In 2005, gas was being transferred to a tank in the Buncefield Tank Depot, and unfortunately that tank overflowed, releasing hydrocarbons which eventually ignited, exploded, and caused a lot of fires, which resulted in tremendous damage, over $1 billion worth of damage from that incident. Now, if we look at the design of that tank, there was a tank level gauge which read out the level in the tank, and that was presented to the operator within the HMI. Now, that tank level gauge was designed to present an alarm to the operator when the tank was full. Unfortunately, that level gauge failed when the tank was 2/3 full, so that when the tank actually became full, no alarm was generated. So we had a failure to enunciate the alarm. No worries though, because we had a second layer of defense, or a second layer of protection, in a high-level safety alarm, which again, once the tank reached its ultimate high level, that safety alarm was supposed to trigger, announce to the operator, enunciate to the operator, and more importantly, trip the valve that controlled the incoming flow of gas. So it would have automatically shut off the flow to the tank. Now, unfortunately, when the level reached the spot where this second layer of protection would trigger, it also failed. So again, we had a couple of things failing in a row, or in consequence, to set up this accident situation. Now, we're going to refer to this incident again during this discussion. So now along comes the new ISA standard on alarm management, released in 2009. One of the main goals was to address the performance issues that we just talked about, as well as to help prevent those accidents that we also talked about. And this standard really provides a framework for an alarm management program. It addresses the design, engineering, operation, maintenance, everything you need to do to put in place an effective and sustain a good, effective alarm management process. It's organized along the lines of a life cycle, similar to the functional safety life cycle, which also leads to creating a continuous improvement approach. And as I mentioned, throughout the standard, one of the goals is really to provide the recipe or the direction for how to eliminate those most common alarm management issues. Now, it's expected to be accepted as good engineering practice by insurance agencies and regulatory agencies such as OSHA. One of the other significant things of this standard, is that for the first time, the discipline of alarm management now has a standard that's comparable and can be laid alongside the functional safety standard, the standard that's been around for a lot longer and is very well established. When we do this, one of the things that we see is these standards, these life cycles, are very similar and very comparable, and in fact they also interconnect in a lot of their stages, which leads one to think that, hey, this would probably make sense to treat these two disciplines or these two processes from a holistic point of view. In particular, in this seminar, we're going to talk about how the alarms that are generated or indicated in the allocation of safety functions to protection layers stage of the safety life cycle, or the LOPA stage, are analyzed or designed in the alarm management life cycle. That's called rationalization. And then we're also going to talk about then how the performance of the alarm management system, which we measure in the monitoring and assessment phase, turns around and affects the actual effectiveness and performance of the safety system. First, let's start with some grounding, and that is, what is an alarm? What's the definition of an alarm according to the ISA standard? It's an audible and or visible means of indicating to the operator. This is a key principle in that the audience, the target of the alarm system is really the operator. So the messaging, the information that's transmitted is for the operator. It's not for the process control engineer or the maintenance person. It's really primarily designed to be for the operator. It's to indicate an equipment malfunction, process deviation, or abnormal condition. So it needs to indicate that something is wrong, and also that it requires a response. And this idea that it requires a response is really one of the most important elements of alarm management. We'll call it the cardinal rule of alarm management. The corollary to it is that if you have an alarm and you can't define what the operator's response is or what they should do, then that point should not be an alarm. So now let's look at a little bit more of what I mean by response and what constitutes a successful operator response. First, the operator needs to be able to detect the alarm. He needs to be able to see it, notice that it's there, primarily probably through the HMI. And if you've ever been in a control room during an upset situation, there's a lot of things going on. So to be able to communicate this important piece of information to the operator is not a trivial task. And we need to focus on making sure that we can get notification to the operator so that he realizes and sees the presence of this alarm pretty much as quickly as possible. Next, I'm having some technical difficulty here. Okay, next, the operator needs to diagnose the situation. He needs to figure out what is the problem and what is the corrective action. What does he need to do to fix the problem? And then finally, he needs to respond, which in this case doesn't mean acknowledging the alarm. It means taking a proactive action to adjust the process or modify the process. So this means opening a valve or turning on a backup pump. And this action or this response may take place in the control room from the HMI, where the operator may need to leave the control room to go out into the field to do this. Of course, that takes extra time. Or he may need to call another operator or a field operator to go and do this. And again, this takes extra time, so it needs to be factored into the overall timeline. Now, alarms and safety instrumented functions are very similar in a lot of respects. They both provide a level of risk reduction. Safety instrumented functions, though, on the other hand, there's many fewer of them in a typical system, on the orders of tens to hundreds in a plant. And they, of course, are evaluated and designed individually. Alarms, on the other hand, you may have thousands to 10,000 of them in a large petrochemical plant, typically in the basic process control system. They are evaluated and designed individually, as well as evaluated as a whole. When the operator responds to an alarm, he needs to check and understand the performance of the whole entire system. So he's essentially viewing the alarm status of all the alarms in the entire system before he operates or works on that one particular alarm. So there's an acknowledgement or an assessment of the overall performance of the entire alarm system, not just respond to an individual alarm. He's got to assess what's going on with the entire system. Now let's talk in particular about LOPA alarms. And again, these are the alarms that are identified during a layer protection analysis, so they're designed to provide a quantitative level of risk reduction. And we'll call these safety IPL alarms. For an alarm to be in a layer protection, it needs to meet the same criteria as every other layer of protection. and to be independent. And to be independent, to be an IPL, it needs to be specific, meaning it needs to be designed or work for a particular situation or initiating event. It needs to be auditable, which means you need to be able to test that it's going to work. This was a big problem with the Buncefield situation, and we'll talk about that a little bit later. It also needs to be independent from the other protection layers as well as the initiating event. And if you think about Buncefield and you think about the tank level gauge failing, that transmitter failing, if that was the initiating event to cause the tank overflow, then the idea that we would get an alarm from that violates this independence. So something else that needs to be factored into layer protection analysis. And finally, it needs to be dependable. The likelihood that the alarm will be triggered and the operator will respond to effectively needs to be high, that will be done successfully. And of course, it's evaluated or designed, its key design parameter is the probability of failure on demand, which is essentially the likelihood that the operator or the alarm is going to fail to be addressed appropriately in time. So now actually let's look at what that probability of failure on demand for that operator response plus alarm layer, for the whole entire layer of protection related to alarms and operator response. And it really consists of two different elements, two components. The first is the probability that the alarm itself will enunciate. And if we remember the Buncefield situation, that tank level gauge alarm failed to enunciate. So that's where that failure occurred. The second part, where we'll spend more focus, relates to the probability of failure of demand of the operator's response. And this is the probability that he's going to fail to successfully detect, diagnose, and respond, those three things we said need to happen, to the alarm correctly and within the allowable time. So those are the two major components. There's a lot of guidance, recommendations on what the assumed probability failures of demand should be when doing a LOPA analysis. Here's one example which shows different levels of performance or different levels of PFD based on design and performance. And it describes the prerequisites or the things that need to be in place to deliver this particular PFD. If we look at category 1, the nominal operator response with a PFD of 0.1, we can see that to be able to take this level of credit or risk reduction, we need to make sure that the operator is properly trained and has sufficient time to respond to the alarm. If we look at the alarm system performance and analysis and believe that those two conditions are not true, then we can't claim this level of risk reduction, and we would actually drop down to category 3. There's other recommendations for PFD in the literature. One example or one good reference is the AMUA 191 guidelines, which again has some performance-based recommendations for PFD. Here describing their recommendations on what PFD to use based on the origin of the alarm and its design. They recommend to not assume a PFD of 0.01 or below, which would indicate that the alarm would be SIL2. They do not recommend using SIL2. And if you look at the ISA, IEC functional safety standards, they actually have recommendations on PFD values as well, typically 0.1 for the operator response to alarms. But what I want to focus your attention on here is the two middle lines, the human performance. And look at the huge variation that exists for the effectiveness of the human performance, the operator's response, when he's trained and not under stress versus a situation when they're very stressed. You can see difference of 4 orders of magnitude between them. And that just goes to show how important human factors are in the reliability of the operator's response. There's been a lot of studies that have been done to describe or document the different factors that influence the operator's response, including, in particular, of course, the workload and fatigue. There was one study done for pipelines that showed that the likelihood that operators of a pipeline will make mistakes increases toward the end of their shift as opposed to the beginning of their shift, which makes a lot of sense, and also is driving the pipeline industry to look at or monitor how long shifts are for operators, maybe capping it at 12 hours a day or no more than 8 hours. Certainly physical condition affects the operator's response, and training, and of course motivation. There's also a lot of factors which increase the chance of making an error in the response to an alarm. In general, humans have a greater chance of making errors when they have to make a quick, important decision under emergency conditions. The U.S. military deals with this all the time and factors this in to their structure and the way they execute battle plans. Also, needing to make multiple decisions in a short time span certainly increases the chances of making an error, and being subjected to confusing or misleading or data that conflicts, like on an HMI display, also increases the chance of making an error. And part of what we're going to talk about with alarm management and the recommendations of the ISA standard is how to minimize those factors that increase the chance of the error. So now let's look at the timeline for the operator's response. We've got our initiating event occurring, and then shortly thereafter, hopefully, the alarm is successfully enunciated. So now let's look at the things that will occur in between the enunciation of the alarm and the hazardous event occurring. And hopefully we'll have everything occur that needs to so that the hazardous event does not result. And we talked about the things that the operator needs to do with detecting the alarm, noticing that it exists, figuring out what the problem is and what they need to do, and then taking the corrective action. So that's the operator's response. Well, once we've completed that, once the operator has completed his response, we're not out of the woods yet, because in many cases the process has dead time and it doesn't respond immediately to the operator's action. So we need to factor in the idea that process needs some time to be able to respond to the action of the operator. So we'll call this the process response time. And then we'll also look at the sum or the maximum time that the operator has to respond in conjunction with the process dead time, and see that certainly we want to make those, the sum of those two time periods, to be less than the process safety time. Process safety time is a term that means the amount of time between the initiating event and the hazardous event. So let's look now at some of these key time parameters, and then we're going to make some relationships between them that will help us evaluate the efficacy of safety IPL alarms. First, let's talk about this maximum time to respond. That's the last moment in time that the operator's action will actually prevent the hazardous event from occurring. Process safety time we talked about is the time between the initiating event and hazardous event. Minimum operator response time is a different parameter. That's the amount of time that as a company or a site or a location you believe you must provide to the operator to them to have a good chance of responding to the alarm. So what we're talking about is something like 5 or 10 minutes. Where you might say, if we cannot provide at least 10 minutes for the operator to respond, then we're not giving them an effective chance to respond successfully, particularly for a safety IPL alarm. So now let's look at how those time parameters can be used to create some rules for evaluating the operator's response. So first we can say that the amount of time that the operator has to respond, to detect, diagnose, and respond, plus the dead time of the process, has to be less than the process safety time, or else the hazardous event will occur. We can also say that the process safety time needs to be greater than the minimum operator response time. So if we're doing analysis, LOPA analysis, and we come across the situation where the process safety time is 2 minutes, and we've decided that based on an operator activity analysis that the minimum operator response time is 10 minutes, then we know that that's not an effective situation because the process safety time is significantly less than the minimum time that the operator needs to respond to that alarm. We can also say that the actual time that the operator has to respond must be greater than the minimum operator response time. And of course, the time that the operator has to respond is affected by the limit that we set for the alarm. And here's an example of how a tool that's used. This is actually Exeda's new cell alarm tool, and how it uses information on the process dynamics, the rate of change, and again the minimum response time and process safety time, all to calculate the potential alarm limit that should be used with a particular alarm. Now, as I mentioned, the time and the alarm limit go together, and we can modify the alarm limit to change the amount of time that the operator has to respond, but there's some trade-offs that go with this. Ideally, we want to create an alarm limit that provides the operator with sufficient time to react so that the process doesn't reach the consequence threshold. And the way we typically calculate that alarm limit is by looking at where the normal operating envelope is, what is that consequence threshold, and looking at the process dynamics. What's the rate of change of the process variable? Now, we could possibly change the alarm limit, increase it so it's closer to the consequence threshold, or reduce it so it's closer to the normal operating envelope, but each of those has its own pros and cons with it. If we reduce the alarm limit and make it closer to the normal operating envelope, then we will give the operator more time to respond. However, we're more likely to have nuisance alarms because we're closer to the normal operating limit. If we get nuisance alarms, that will decrease the operator's confidence in the system overall and have the reverse effect, essentially, than what we really want. Similarly, if we increase the alarm limit closer to the consequence threshold, that will give the operator less time to respond. They'll have more confidence that when the alarm occurs, it truly means something, but he's got less time to respond, and his likelihood of a successful response is reduced. Now let's shift gears and talk about how the ISA standard on alarm management provides guidance that we can capitalize on to minimize the probability of failure on demand for a safety IPL alarm. And what we're going to do is look at some of the key stages of the alarm management life cycle and distill out key actions or key things that we need to do to optimize the alarm system performance. Now, we don't start any alarm management plan without first talking about the need for an alarm management philosophy document. This is the overriding document that describes how a plant or site will execute alarm management, provides the rules and guidelines for how you will prioritize alarms, what is an alarm. It'll provide rules for how you design the HMI, your performance benchmarks. And many folks that are starting to see this alignment between the safety and alarm management life cycle have started to think about rolling their alarm management philosophy into their functional safety management plan, which is a great idea. Now, having this philosophy document done and in place is a prerequisite before you can execute other tasks in the alarm management life cycle, such as rationalization, which is what we're going to talk about next. And this is when we look at all the alarms that exist in the database and determine, review them, and justify that all those conditions are truly alarms or need to be alarms. We're going to compare them against the criteria for an alarm, the definition for an alarm that we talked about earlier, where that's defined in the alarm philosophy. And when it comes to alarms, more is not better. So what we're trying to do is create the minimum set of alarms that's needed to keep the plant safe and within the normal operating range. So what we'll do is, for each alarm, ask ourselves a series of questions. First being, what is the potential consequence if this alarm was not acted upon? And by that I mean the immediate consequence. If there's no consequence, then there's no alarm. Just like if there's no corrective action, there's no alarm. We also talk about the time to respond, which we use to determine the priority, and we'll document the cause and the corrective action, determine the limit, and classify it. All this information is stored in something that's called a master alarm database. Now, rationalization has a lot of significant benefits. It is a resource-intensive activity, but if we go back to the performance benchmark that I showed earlier from the ethylene plant in Houston, that alarm management program that they implemented, the majority of the performance improvement that they saw was based on performing a rationalization of their entire database. So they saw a significant reduction in the number of alarms presented to the operator. They saw less nuisance alarms, eliminated redundant alarms. That also increased the operator's confidence in the system and its integrity, and the operators knew that the alarms were prioritized in a way that if they got a high priority alarm, they knew that they needed to operate on that first. In fact, prioritization is one of the key activities during this rationalization process. Because priority is the attribute that operators look at to determine which alarms they need to respond to first. Alarms are typically prioritized based on severity of consequences and the time available to take the action. And here you can see an example of a matrix showing alarm priorities as a function of those two things. This type of a matrix, the goal is to end up with a distribution of alarm priorities where we have a very minimum of them being high priority on the order of 5%. Now here's an example of how the Exida SIL alarm tool would execute prioritization. For this example, for this customer's situation, we've evaluated the potential consequences in the area of health and safety, economic, and environment. And those might sound like conditions or areas that you would consider during a HAZOP or a LOPA. And if you make that connection, that's correct. What we actually want to do is, when possible, use the same consequence matrix that exists for those activities and use that for alarm management as well to help us set the priority of the alarm. So here, this particular customer has defined the thresholds for the different consequence levels. He's also set his operator time to response areas as less than 10 minutes is not an alarm. So he set a minimum operator response time of 10 minutes, which means if it's less than that, then that's not a valid alarm situation. Then we've got 10 to 30 minutes and greater than 30 minutes. Rationalization is also the time or the stage in the alarm management life cycle where the design details of the safety life cycle really come in or brought into the picture. In particular, the results that come from a LOPA analysis or a HAZOP analysis, and here we see an example of how a tool might import that information and have that available during the rationalization process to understand the significance of an alarm from a safety design point of view, including linkage, potential linkage right directly to the safety tools, and you see a checkbox for indicating that it is a safety IPL alarm so that we can keep track of that and pay special attention to those alarms. And this idea of keeping track of alarms, the type of alarm, and special attention is what's called classification, which is another key element of the alarm management life cycle. And here we want to classify each alarm as a way of helping us to organize and manage them all. Classification is not an attribute for the operators to use. It's really for the designers and managers of the system. And what we're going to do is we're going to classify each alarm potentially based on how it was identified. Is it a safety alarm? Is it environmentally critical? Was it identified in an environmental permit? Is it a quality-related alarm? And based on this identification, that's going to kind of set some of the key requirements for how we'll manage it. And what I mean there is the frequency of training and testing and how often we'll audit the way we analyze and handle those alarms and management of change. So for example, certainly a safety IPL alarm, an alarm that's identified in a LOPA, the frequency for testing that alarm is definitely going to be much higher and much more critical to pay attention to than a general alarm. So that's the idea of classification. Another important element or way to maximize the risk reduction that we get is to design the HMI to promote situational awareness. One of the problems with the Buncefield situation was, although the tank level gauge failed, there should have been information on the operator's screen to see that there was a mismatch in data. For example, if there was a trend of the incoming flow versus level, then one might have seen that, hey, the flow rate is non-zero, but my level is steady, something's wrong. So that level of situational awareness was not provided for the operator. So the HMI design is really important for that, as well as to help the operator detect, diagnose, and respond to that alarm. And here we've got two different examples of potential HMI designs, one on the left and one on the right. The one on the left does not follow best HMI practices, and what we want to have happen here is that when an alarm occurs, it jumps off the page at the operator. And you can see that the HMI screen on the right, where we've got two alarms in their own unique colors and blinking, certainly draws your attention much better than the one on the left, which my attention is drawn to the blinking devices, as well as is drawn to the colors of the different piping and not to the alarms. So we can see a couple of the alarm management HMI design recommendations demonstrated by these two graphics. First is that colors that you use for alarms should be reserved for alarms only. The screen on the left, we can see that alarms are yellow, and then there's also a piping line for fluid that's yellow. Well, that's going to be very confusing. We want the situation to be set up like it is on the right, where we're using dedicated reserved colors for alarms, and when you see that color, that's all it means. It's not used for any other purpose within the HMI. Now, you also can't rely on color alone, because there are colorblind operators in the control room. So you see on the right that we've got multiple methods of enunciation or getting that information through to the operator with colors and blinking and patterns. We've talked about how important training is. Operators really need to know what to do when the alarm occurs. Just about all of the information that we looked at previously related to what PFD you can claim is predicated on a level of operator training. So it's really important that that be addressed in an alarm management philosophy and program, because it truly is linked to the level of risk reduction. Now, of all the alarms that you want to pay attention to for a training program, certainly safety IPL alarms have got to be some of the most critical, because they're not going to occur very frequently, or hopefully not very frequently, and when they occur, it's typically going to be in the midst of a lot of other things going on. So during a significant process upset, you'll probably have a lot of alarms, a lot of people in the control room. So the more training that the operator has had to respond or how to respond to those safety IPL alarms, the better his response will be, and essentially effectively keeping that low PFD value. Another recommendation from the ISA standard is to make alarm response procedures available online. Of course, this will help the operator respond to the alarms. That's the goal here. When we talked earlier about rationalization, we talked about documenting the cause of an alarm, the consequence, the operator action. Well, all that information obviously would be very valuable to present to an operator when an alarm occurs. So when a certain alarm occurs, let's pop up the information that we defined during rationalization related to that alarm and present him with that information, which should significantly help him diagnose and perform the corrective action quicker and more accurately. So that's the goal of this And one of the capabilities that we've built into our new tool is to take the information that's recorded during the rationalization process, the corrective actions, the how do I confirm that this is truly an alarm condition, all that information, and get it into an individual report that then can be displayed within the HMI. So a particular alarm occurs, the operator can call up his alarm response report for that particular alarm and get that information to help them make their response. Maintenance and testing, of course, are also very important to ensure the integrity of those safety IPL alarms. And the best method, and ideally what you're doing with the testing, is to verify the enunciation of the alarms. You're addressing that failure mode. Ideally, you also want to include the operator's response, if at all possible. Then you're testing the full layer of protection. And of course, safety IPL alarms, due to their critical nature, would probably be part of an OSHA mechanical integrity program. Now, again, referring to the Buncefield example, that second level of protection, or that second layer of protection, the high-level safety switch, one of the issues with that was that it really was untestable or unauditable. It was located on the top, the roof of the tank on the inside, in a location that really couldn't be accessed to test. And the only time it could be tested was if the tank was full and overflowing, essentially. So there was really no good method of testing that in situ alarm, which meant we couldn't verify or audit its performance. We also need to measure, of course, the alarm system performance as the key means of determining or analyzing whether we're going to get the PFD from the system that we want. And we want to compare key performance indicators like the alarm load on the operator. That's one of the key elements we want to do. But we can also identify the alarms that are being problems. Nuisance alarms we can identify, chattering alarms, stale alarms. In other words, we can analyze and see which symptoms or which issues we have and what are the particular alarms that are causing them, so that we can go back and fix them or redesign them through the rationalization process, thus kind of creating a continuous improvement process. Now, in addition to general monitoring of overall performance for the whole entire system, we can also look at what's going on with particular safety IPL alarms. Because certainly if we see that there's a safety IPL alarm that's being triggered every day, or that the operator is disabling it, changing its limit, or suppressing it, then we know we've got an issue, and that alarm is not going to provide the risk reduction that we're counting on. We can also look at those results to help us estimate initiating frequency. So now let's look at some of the performance metrics from the ISA standard, looking at the number of alarms that occur in a certain amount of time, 10 minutes, an hour, a day per operator. The number of alarms that occur in a 10-minute period is indicative of an alarm flood scenario. So how many alarms occur when a flood occurs, how many are actually being presented to the operator, what's the percentage of time that the system is in flood. We want to minimize the contribution of the most frequent alarms, because they're typically going to cloud the operator's view. We want to drive the number of chattering alarms or fleeting alarms. These are alarms that go in and out of alarm on high frequency, like 3 times per minute. We want to drive that to 0. We also want to reduce the number of stale alarms. These are alarms that stay active for more than 24 hours. We want to drive that to 0 if possible as well. And then look at also the distribution of alarm priorities. We can't have all the alarms be high priority. It's impossible to treat them that way and respond to them. So we want a small fraction, around 5%, to be high priority, and then that will help the operator respond accordingly to them. Now, there's tools to automate the analysis of the alarm system performance, and Exida has entered into a partnership agreement with LogMate, with TIPS, the company that makes the LogMate software, and in that software you can measure all the alarm system performance metrics and look for those alarm issues and pinpoint the alarms that are causing them. So with that, I think I'm going to jump ahead to the conclusion then and kind of recap where we were and what we talked about. And the important takeaway message is that the alarm system design and performance really can affect the operator's ability to maintain the plant safety and his ability to respond to the alarm, to detect, diagnose, and respond to a safety IPL alarm. It certainly affects his probability of failure on demand and the enunciation of the alarm, and certainly the operator's response to that alarm, to the safety IPL alarm. And if you've got poor performance, if you're a key element of maximizing or PFD or minimizing the PFD is to monitor the alarm system performance. In the event that you do have poor performance, try and fix that. And some people would go as far as, if you've got poor performance, then you need to consider downgrading the risk reduction provided by those safety IPL alarms. We've also seen how the ISA-18.2 Standard provides us a lot of suggestions and recommendations on things that we can do to help get the most out of the safety IPL alarms and essentially minimize their associated PFD, and also make sure that that PFD or that risk reduction is actually delivered in practice. And finally, hopefully you've all seen some reasons why it makes sense to treat the alarm management and functional safety life cycles, or those activities, holistically together. Certainly treating them together can reduce or increase plant safety, can reduce cost and risk, and deliver better operational performance. So a lot of reason to start thinking about those two disciplines together and holistically. And with that, I'll open it up to questions. If you've got any questions or comments, feel free to enter them into we have one question, which is, what are the minimum times for operator response commonly used for considering them as an IPL in a LOPA? I mentioned 10 minutes. That's a good question. So to conduct a LOPA, we need to establish what is the minimum operator response time to be able to consider an alarm as an effective layer of protection. That's going to be different depending upon the situation and the operator's activity analysis. Do they need to leave the control room? Do they need to contact somebody else to typically go execute an action? So some people set 20 minutes as that threshold. One of the companies that we've worked with has set 10 minutes as that threshold. It really depends on the situation. But the idea of establishing what that is based on how the operator does his job, and then sticking to that and saying, if we can't provide this amount of time for the operator to respond, then a particular alarm is not a valid layer of protection, is an important premise to take with you. Any other questions or comments? I see a comment from Sandeep. Thank you very much. And just for further reference, this presentation will be posted on Exeda's website. And if you're interested in getting a copy of it, please send me an email, and I'll send that out to you. And my email address is shown on the screen. So with that, I'll say thanks to everybody for attending. Have a good rest of your day, and look forward to you joining one of the next future Exeda webinars.